Hello everyone, welcome back to Algebra 1 with Miss Betsy. I'm glad that you're along for the ride with us today. We are going to be continuing our discussion of relations, functions, and graphs, and we're beginning to discover how to show the graph of a linear equation or a straight line today. We will not be using the slope-intercept form of a line or the point-slope form of a line yet. That will be on our next several lectures, so this, for those of you who are not in my class, this might be too elementary of a video for you to watch, but welcome to come along and join us on the ride. As always, I'm using Algebra 1 for Christian Schools, published by Bob Jones University Press. We are at the second edition. We're in section 6.4, which is on page 234. And of course, we have to have a lame joke. We have piggy riddles today, and I forgot to open up to the page that I wanted to use, so now I have to find it. Okay, here it is. What is large, pink, and hairy and stomps around the swamp? It is Pigfoot. So, well, you know what? I took a little bit of a fall yesterday. I'm caring for some animals for a friend of mine, and I sort of went down in their chicken coop, which was quite humorous, but I was holding on with my left hand and managed to sprain my wrist a bit. So if you see me grimace, it's no big deal, and I'm just having to remember not to try and use that wrist too much. Anyway, section 6.4. What we've been talking about up to now, we've been discussing relations and a specific type of a relation which is called a function. All a relation is that there is a relationship between two items. And we've said that we can define a relation by using something called an ordered pair. And ordered pairs are written in the form X and Y. And they're included in parentheses like this, where the X represents the location of the number on this Cartesian coordinate system on the x-axis. The y represents the location of this point on the y-axis, which is our vertical line up and down, and it's called an ordered pair because order is different. For example, if we have this ordered pair here, 2, 4, this tells us that on the x-axis we're going to move over to the point 2, 2, and then we're going to move 4 units up in the direction of the positive 4. 1, 2, 3, 4. So this right here, I'm not going to label it because I want to use this graph later. But this is the location of the point on the plane indicated by the ordered pair 2, 4. Now order, like I just said, is important because the way that you define ordered pairs is not commutative, if you will. Remember, we've learned that when you add numbers together, when you multiply numbers together, those two operations are commutative because 2 times 4 is the same as 4 times 2. 3 plus 6 is the same as 6 plus 3. However, the location of the point 2, 4 and the location of the point 4, 2, those are unique, distinctly different locations. Here, where we've changed the order of these two numbers, we have 4, 2. So here we would go over 4 units on the x-axis, 2 units on the y-axis. And you see that we have identified 2 totally different locations. So relations are, all a relation is, it's a set of ordered pairs that indicates that there's a relationship between numbers, between items, between prices, and different types of fruit. That's all a relation is. Then we also spoke about a function, and a function said that for every x value, there could only be one y value. So this is what we've been working about so far. Let me read a little bit from our book. It says, many relations and functions can be described in terms of an equation. One such equation is called a linear equation because when it's graphed, all of the points that, all of the ordered pairs that make that equation to be true They're in a straight, you can actually see that they lie on a straight line. And they have a particular form of that equation. This is called a standard form of the equation of a line, and this is what it looks like. Standard form of the equation of a line. This takes the form ax plus by is equal to c, and a, b, and c are all real numbers. Positive, negative, fractions, decimals. This is our pattern for what a linear equation looks like. An example of a linear equation would be 3x plus 2y is equal to 7. And in just a few more days we're going to learn that it's very, very quick and easy to say, okay, if I have this equation that has an x and a y in it, I can do just a little bit of manipulation to that, and I can very quickly show you what that picture is going to look like, what that straight line is on a graph. But before we get those little bit of shortcuts, we've got some basic information that we want to learn first. So before I get started talking about that though, I want to review what I have up here. I want to review the Cartesian coordinate system. What the Cartesian coordinate system does is it allows us to locate any point anywhere on a flat surface in a plane by using an ordered pair to indicate its location. We go to x is 1, y is negative 4. We have the ordered pair 1, negative 4. That lets us identify one particular point in this infinite plane that goes forever. And remember, a plane's not something that you fly, but a plane is, just think of it like a thin sheet of glass. It really has no thickness, but think of it as a thin sheet of glass that extends forever in all directions. That's our Cartesian coordinate system, or our Cartesian plane. The Cartesian coordinate system allows us to locate any point anywhere in that plane. This horizontal line, we began to plot numbers on a number line at first. The horizontal line is just like a number line. This is what we call the x-axis. And that's where we're going to plot our x point in our ordered pair. This vertical line intersects the x-axis perpendicular. It intersects it at the origin. This is called the y-axis. Numbers above the x-axis are positive, below the x-axis are negative. It's similar to what it's the idea behind a vertical thermometer. The higher up that mercury goes, the hotter the temperature is. The lower the mercury drops, you're moving into negative temperatures. Fortunately, here in Texas, we don't deal with those negative temperatures very frequently, but we do sort of top out the mercury as far as the heat goes in the summer. You'll see that the intersection of these two axes here divides our graph up into 4 sections. These are called quadrants. We have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And you do use Roman numerals to identify these quadrants. And by breaking it up into these 4 sections, you'll see that the sign of all of the numbers in the ordered pair in each quadrant is the same. What are we going to have here? All of our x values are positive. All of our y values are positive. So ordered pairs in the first quadrant are both positive. The sign of both of the terms is positive. In the second quadrant, our x values are going to be negative, but our y values are positive. Third quadrant, both the x's and the y's are negative. And finally, in the fourth quadrant, we have a positive x and a negative y. So that's just a brief review of what our Cartesian coordinate system is. So let's dive right in. We have an example here This is on page 234. I'm going to change it just a tiny little bit. Your book says graph the set of all ordered pairs x and y such that y is equal to x plus 5. I'm going to change it to x plus 1 because that makes it fit onto my graphs a little bit better. But one more thing that I wanted to mention about these graphs that I've drawn here. When you are doing your homework or your test or whatever, you put one and only one graph on each coordinate system. You don't draw me like, do all of your homework on just one graph. Okay? This is where you're going to want to be using your grid paper. You want to use a straight edge, label your the locations of your points 1, 2, 3, 4, 5. Doesn't have to be 1, 2, 3, 4, 5, but the divisions have to be even. Like I could have counted 2, 4, 6, 8, 10 if I needed to be able to graph the points more compactly, but I have just set up right here 3 separate graphs that I'm going to be using. You also notice that I have arrowheads at the end of each end of the axes. You have to put that there because that arrowhead indicates that this line extends out forever. If you don't have the arrowhead, you just have a little piece of the plane and you've not been technically correct. Okay? Back to here. Our example says graph the set of all ordered pairs x and y such that y is equal to x plus 1. Remember, I'm changing that a little bit. Graph the set of all ordered pairs such that y is equal to x plus 1. So what are we going to have to do in order to be able to come up with some ordered pairs? Well, we have to make sure that our equation is solved for y, and we already have that. So now what we're going to do is make a table of ordered pairs. Y is equal to x plus 1. And when we're plotting points, in order to draw the graph of a straight line, you have to have at least 3 points. And when you're just coming up with random points here, well, we could say, let's see what happens if x is 19.3, or if x is minus 2,000, or if x is 3 million. We're going to be able to come up, of course, with the value for what y is, but it's not real helpful when it comes to graphing that line in very limited space. So it makes sense to be wise with what you select for your trial values. For example, how about if we have x is 0? If x is 0, then y is going to be 0 plus 1, which is equal to 1. That's easy. How about x is 1? Then y has a value of 1 plus 1, which is equal to 2. Now I might say, what happens if x is 2, or what happens if x is negative 1? I think I'll go ahead and put x is negative 1. When x is negative 1, y is equal to negative 1 plus 1, or y is equal to 0. We now have 3 points, and we can graph these 3 points. We're going to plot them. What are the points here that we're graphing? Remember, we're looking for a set of ordered pairs, x and y. X is 0, y is 1. X is 1, y is 2. X is negative 1, y is 0. So you can take your ordered pairs directly off this chart. For this example only, I'm just going to write our set of ordered pairs. We have a set of 3 ordered pairs here, 0, 1, 1, 2, and negative 1, 0. Okay? I'm going to plot these points on my first Cartesian coordinate system. So this is like example 1, where I've tweaked it just a little bit. 0, 1, if x is 0, y is 1. If x is 1, y is 2. If x is negative 1, y is 0. And you would want to make sure that you identify the location of these points. So this is 0, 1. This is 1, 2. And this point down here at the bottom is negative 1, 0. We've plotted our points and we have labeled them. And I'm going to sneeze. Excuse me, I'm sorry about that. I really wish I had a remote for the video, but I don't. You notice that these 3 points are on a straight line. So now you want to get your straight edge. You carpenters in the group, I have a small level here. That I'm going to use for my straight edge. And when I'm drawing the graph of a straight line, I want to connect the dots. I want to make sure that I'm crossing the x-axis and the y-axis. And then I want to make certain that I have added an arrowhead onto the end of that graph. The final thing that I want to do now is label this line with the original equation. And I have y is equal to x plus 1. So this is how you can now see that you have an equation. This is a linear equation because when you plot the points that solve it on this straight line, on a Cartesian coordinate system, you get a straight line. Well, just for grids, let's see. I'm looking right here, and this point is on the graph. Let's just see if that actually satisfies this equation. What are the coordinates of this point here? X is 3, y is 4. Does this satisfy our equation? If x is 3, is y equal to 4? Yeah. 3 plus 1 is equal to 4. So that's where these graphs are really neat, that you have a visual of what your equation is. So let's go ahead and do a second graph here. And this is going to be example 2. But first, we've got a little recipe, well, a little algorithm that they give you for what do you do if you're going to graph a linear equation. And this is when all you're doing is plotting points. So let me go ahead and write these down for you. If you want to graph a linear equation, the first thing that you need to do is solve the equation for y. Very first thing, in our example that we used, the equation was already solved for y, so we didn't need to do that. Now we want to make a table of ordered pairs, and we want to select at least 3 points. Pairs. Use at least 3 points. Sometimes you might want to get a 4th one, but I'm having a hard time thinking of when you might actually want that 4th point, because from basic geometry there's, I believe it's a theorem or a postulate that says any 3 points determine a line. You can connect any 2 points with a straight line, but once you get a 3rd point on that same line, there's no other line except that will contain those same 3 points. So our third thing says to graph the ordered pairs on a Cartesian coordinate system. So I'm just going to say plot points on Cartesian graph, which is exactly what we did. We took our 3 ordered pairs and we plotted them on the graph. Now we're going to connect the points with a straight line. Now remember, when I was talking about why order is important, why the point 24 and the point 42 are not the same point, and I did these little dots here. Here's the point 24. Let's say that we had a point of 0, 1, 1, 2, and then we had this point 24, and you tried to connect those with a straight line and you couldn't do it. When you're finding possible points for your graph of these straight lines, it's sort of self-correcting. If you can't line up those 3 points with your ruler, then you know that you've done something wrong somewhere. You go back and you recheck your calculation, because those 3 points have to be on the same straight line. And finally, once you've connected them with a straight line, you label the line with the original form of the equation, with the original in our case that we had with our first example here, our original form of the equation, we didn't have to manipulate it because it was already solved for y. We said y was equal to x plus 1. So this is what you're going to do in this chapter. When you're graphing a linear equation, you're going to make sure that first you solve it for y, then you create a table of ordered pairs. You have to have at least 3 ordered pairs. You're going to plot those points on your Cartesian coordinate system. You're going to connect them with a straight line. If those 3 points do not connect in a straight line, you know you've done something wrong. Once you have a straight line drawn, then you're going to label that line with the original form of the equation. Okay? So now let's go ahead and do example 2. And our instructions say this. They say to graph x plus 3y is equal to 4. Now all of a sudden this looks a little bit different. Last example we did, we used our set builder notation, and it asked us to graph the set of all ordered pairs x and y such that y is equal to x plus 1. We already know that when we graph this, that we're graphing a collection of ordered pairs, so we don't have to go to set builder notation at all. We can move right on to our next step. Those 5 steps that I just erased for you, hopefully you can refer back to those in your notes. First it said, solve each equation for y. We're going to solve for y, we're going to subtract an x from both sides of the equation. X plus 3y minus x is equal to negative x plus 4. Now, does that look all right to you? Well, yeah, because subtraction is the same as adding the opposite. A lot of people prefer to have your x in front of your constant term when you are solving an equation. So this would give us 3y is equal to negative x plus 4. Now, could I have had this look differently? Could I have said x plus 3y minus x is equal to 4 minus x, so that I had 3y is equal to 4 minus x? Do those 2 equations mean the same thing? Yes, they do. Does it matter which form you use? No, but I do think that it's a good idea for you to get in the habit of using your variables first with your constant term last, because that's the standard way to write an algebraic expression is to have all of your variables first, followed by your constant term. So am I going to mark it wrong if you say 4 minus x? No. Do I prefer negative x plus 4? Yes, I do. Okay? So moving right along now, I'm going to get rid of that example here. Now we have to divide both sides of the equation by 3. And we have y is equal to negative x plus 4 over 3. And once we have solved this equation for y, we can create a table of ordered pairs, which is exactly what we're going to do. Y is equal to negative x plus 4 divided by 3. We have our table of ordered pairs. We have y is equal to negative x plus 4 divided by 3. So if you will look at your book on page 235, you're going to see that in our table here we've selected very specifically 4 different points. First off, it's always nice to have what happens if x is 0. So if x is 0, y is going to be the opposite of 0 plus 4, the opposite of 0 plus 4 over 3, or it's going to be 4/3. Okay? Now, what can we do? What happens if we say, okay, let's have x be 4. Why do I want x to be 4? Because 4 plus its opposite, any number plus its opposite, is always equal to 0. So this gives us a convenient number to put in, and we have 0 over 3, which is equal to 0. So this is what's called making wise choice of the points that you select randomly. And finally, let's see, how about if we do a 1? If we put a 1, we have the opposite of 1 plus 4 over 3 gives us 3 over 3, which is equal to 1. Could we have used other values here for x? Sure, you can use any value that you want to, but these here are convenient values to use. What do we need to do now? We need to plot our ordered pairs. And I told you that only this last time was I going to make a set that showed the ordered pairs. I'll just go ahead and do this right now for this example to show that we do have 3 ordered pairs. We have the first ordered pair is 0 4/3, second is 4 0, and the third is 1 1. What we're going to do now is plot these points over here on this graph that we're going to label example 2. If x is 0, y is 4/3, so we're going to guesstimate that. That's the point 1 1/3, which is 4/3, but we're not using improper fraction. We're not using mixed numbers, we're just using improper fractions. Our next point that we're plotting, x is 4 and y is 0. Our final point, when x is 1, y is 1. And we're going to be careful that we label all of these points. Now, we have 3 points, and it sure looks to me like they're on a straight line. Let's connect them, see if we can connect them as a straight line. Sure enough, we can. So we know that we've done our algebra correctly because our 3 lines do connect, and our 3 points connect in a straight line. What's the last thing that we do? We want to label the graph with the original form of the equation, not with y is equal to negative x plus 4 over 3, but with the equation in standard form, which is x plus 3y is equal to 4. It's our second example here that we have graphed. What you can see from this second equation here that I want to point out is you're going to see exactly where the graph of the line crosses the x-axis. You see where it crosses the y-axis, and these 2 points are very important points. It's called the intercept. If it crosses the x-axis, it's the x-intercept. Where it crosses the y-axis, it's the y-intercept. And these are very important points, very useful points. And we're going to learn a little bit more about them in a moment. The y-intercept in particular is very, very important. It lets you graph the equation of a line very, very simply. What I want you to notice is the y-coordinate for the x-intercept here is 0. The x-coordinate for the y-intercept is 0. And that is an important thing that you're going to learn. I think I threw my eraser on the floor. So while I'm erasing this information, you can go ahead and turn to the next page in your text, which is page 236. And we're just going to write out what I said. Make sure that you know exactly what this is. The y-intercept this is the location where the graph crosses the y-axis. It's y-axis. And when we say it crosses it, it also intersects it. Intersect is what you're going to hear most frequently when you're not just initially being taught about y-intercepts and x-intercepts. And this right here, the x value is always 0. Any place, wherever it is, if the graph of that line is crossing or intersecting the y-axis, the x-coordinate has to be 0. No other way to get around it. Now, if we have the x-intercept that we want to talk about, you can already, I'm sure, look at this example, look at these definitions that I have up here, and tell me what these 2 points are going to be, can't you? Well, of course, the x-intercept is going to be the location where the graph of the line crosses the x-axis. Graph crosses the x-axis. And what value are we going to know? What are we going to know about the y-coordinate? If our graph is intersecting the x-axis, the y value is the y-coordinate, or the y value in your ordered pair is always 0. So we have the y value is always. So do not ever tell me when I say, okay kids, tell me the y-intercept, tell me the coordinates of the y-intercept, and you say, well, the y-intercept is the ordered pair 2, 3. No, it's not, because the ordered pair 2, 3 is up here. And I don't even have to plot that point to know that it's incorrect. Why is that? Because you told me that the y-intercept had an x value of 2. Never does. The x value for the y-intercept is always 0. The y value for the x-intercept is always 0 as well. So, I believe what I would like to do now is this last example. Matter of fact, I'm not going to do example 3 because what example 3 did is it showed us where, we're talking about how we identify the x and y axes, but I am going to show you how you can find the x and y values, the x and y intercepts, without having to graph them. Say that we have this equation here, x plus 3y is equal to 4. And they say find these x and y intercepts, how are they going to say it? Find both intercepts without graphing. How are we going to find the x-intercept? How are we going to find the y-intercept? Well, if we have the x-intercept that we want to find, the y value has to be 0. So you substitute in a value of 0 for y, and you have x is equal to 4. So the x-intercept, for the x-intercept, the y value is 0. When you substitute in 0 for y, you figured out that x is equal to 4. I'm having a hard time today. I keep writing ahead of myself. The x-intercept is the point 40. Is that true? Well, yeah. You can look at the graph over here that we've already drawn and see that the point 40 is the x-intercept. What's our y-intercept going to be? Remember we said with the y-intercept, the x value is always going to be 0. So we're going to substitute a 0 for x, plus 3y is equal to 4. 3y is equal to 4. I'm going to divide both sides of that equation by 3 to tell us that y is 4/3. So the y-intercept is the ordered pair where you have an x value of 0 and y is equal to 4/3. Now, is that true? Here's where we graphed this equation right here, x plus 3y is equal to 4, and sure enough, if x is 0, y is equal to 4/3, and that is our y-intercept. So this is how you find an x and y-intercept without graphing. You just substitute in values of 0. Now, what I want to do quickly for you now is just one example from the book, very easy example from the book. We're going to do example number 1. 2x plus y is equal to 5. 2x plus y is equal to 5. And what do our instructions tell us to do? It says, for each equation, make a table of 3 ordered pairs. Then graph the equation on its own set of axes and give the y-intercept for each graph. So this is going to be our number 1 on page 236. Use a clean graph for each problem that you're given, unless your problem specifically says on the same graph. And it's very rarely going to say that. Okay, what's the first thing that we have to do here? Well, we want to solve this equation for y. So we don't need to have the 2x, do we? So we're going to subtract the 2x from both sides of the equation. Subtraction is the same as adding the opposite. Negative 2x plus 5. Y is equal to negative 2x plus 5. We now have solved our equation with a value for y. Now what we need to do is create a table of ordered pairs, and y is equal to negative 2x plus 5. Once again, I want to be pretty wise. I don't want to pick 7/22 and minus 300 as possible values for x. Even though those would give us a value for y, it's not going to help us graphing it on this little piece of the plane right here. I'm going to pick x is 0. So if x is 0, that's negative 2 times 0 plus 5. So x is equal, the y value here is 5. Now I'm going to pick a value of 1 for my x. I'm going to say negative 2 times 1 plus 5 is equal to 3. Negative 2 plus 5 is a negative 3. And now I'm going to pick an x value of 2. Negative 2 times 2 plus 5 is equal to 1. Negative 2 times 2 is negative 4 plus 5 gives me a y value of 1. I have 3 ordered pairs that I can plot here. I have first 0, 5, 1, 3, and then the ordered pair 2, 1. So I have 0, 5, I have 1, 3, and I have 2, 1. So we want to go ahead and label these points. This point here is the point where x is 0 and y is 5, x is 1 and y is 3, x is 2, and y is 5. We want to go ahead and use our straight edge and connect these points. If you cannot connect them in a straight line, your calculations are wrong somehow. Use a straight line, arrowheads at the end of that to indicate that this line extends forever in both directions. Now, label this line with the original form of the equation, which is 2x plus y is equal to 5. This is the original form of the equation. Here is how we solved the equation for y so that we could plot our points. This is how it needs to be identified. Are we finished now? Well, let's see. For each equation, make a table of at least 3 ordered pairs. We did that. Then graph the equation on its own set of axes. We did that. Ah, you forgot this part, didn't you? It says give the y-intercept. What's the y-intercept? The y-intercept is the location intercept. It's the point where the graph intersects the y-axis. And you also know that the y-intercept has an x value of 0. So our y-intercept is the ordered pair 0, 5. This is what your homework should look like when you're graphing lines on a set of axes. It's not hard, but it is time consuming a little bit. I want you to be very neat and make sure that you're giving me this type of work, okay? That's all we have for section 6.4. You all have a great day. I'll see you next time.